everyone, this is Lesson 6, Weathering in Sedimentary Rocks. We are going to be covering two different chapters, and I'm going to break this video into two smaller sections so the material's a little bit more manageable. So first we're going to talk about weathering, which will be in Chapter 6. The next video is going to be Sedimentary Rocks, and that's Chapter 7. So let's dive right on into our weathering. Alright, so first we're going to talk about the different types of Earth's external processes. So first we have weathering, which is the physical breakdown and chemical alteration of rock at or near Earth's surface. We have mass wasting, which is the transfer of rock and soil downslope under the influence of gravity. We'll talk a little bit more about that in Chapter 11. And then we also have erosion, the physical removal of material by mobile agents such as water, wind, or ice. Now, without Earth's external processes, no sediment would ever be created to produce our sedimentary rocks. So these are vital to actually producing and creating our different types of rocks that we'll talk about more in our next video. Alright, so there's two different types of weathering that we'll focus a little bit more on. The first type is what we call mechanical weathering. So this is breaking of rocks into smaller pieces. So you're actually reducing the surface area. So there's four main different processes. We have frost wedging, and that's what we see in this upper image. Let me just grab my pen. So we have frost wedging right here. So frost wedging and thermal expansion, these two kind of go hand in hand. So as we have these different rocks, we have water that's getting in between them. It's freezing and expanding. Water can expand up to 9%. That's an incredible amount. So as it's expanding, it's breaking and pulling those rocks apart in all different directions. Now, the image directly next to it shows the impacts that frost wedging and thermal expansion can have on different materials. Now the next type of mechanical weathering we'll talk about is what we see down here, and this is what we call unloading. So it happens in several different phases. So the first one, we have some sort of mass that's underground covered by lots of sediment. Now, over time, there's erosion. That sediment is removed. It brings that mass up to the surface, and that's what we see in image 2. As it's being brought up to the surface, it's getting exposed to everything that's happening there, and unloading is going to start leading to sheeting. So it'll actually form little sheets that you can see over here, and they're just sliding right off this domed structure. Now lastly, we have our biological activity, and that's what we see over here. And so a great example of this is that there's some sort of seed sapling that gets in a crack of a rock. As it starts to grow, the root structures will actually start to split and pull that rock apart, and it can break down different types of rocks that way. So mechanical weathering is really aiding our chemical weathering. So mechanical is breaking the rocks into smaller pieces. It's reducing the surface area. So then our chemical weathering can really start to eat away at the smaller pieces. So if I were to give you two different types of materials, let's say I gave you a boulder and I gave you gravel, which one do you think is going to weather more quickly? It's going to be the gravel because it has a smaller surface area. It allows much more processes to affect it than something as large as a boulder. Alright, so let's talk about our major processes of chemical weathering. So this is the breakdown of rock components and internal structures of mineral. So the most important agent is going to be water. So we have dissolution, oxidation, and hydrolysis. Now dissolution is aided by small amounts of acid in the water, so soluble ions are retained in the underground water supply. So it's slowly dissolving it. Next, we have oxidation, which is any chemical reaction in which a compound or radical loses electrons. This is important in decomposing ferromagnesian minerals. So again, when you're dissecting these words, ferro we know as iron, magnesium, and so these are going to be our dark colored silicate minerals. Next, we have hydrolysis, which is the reaction of any substance with water. Hydrogen ions are attacked and then replaced by positive ions. So this image over here, this is where we have dissolution occurring, this marble statue, it's slowly dissolving it. Our next image, our middle image, is where we have oxidation occurring, and you can see that there's this little rind or a ring, and we have this red color here and our white color here. So this is the unaltered rock there in the middle, and then it's slowly oxidizing out on the surface because the ferromagnesium minerals are decomposing and essentially it's rusting in place. And then lastly over here is an example of hydrolysis. So it's being reacted with water and you can see that it's creating that pitting that you see. Alright, so a little bit more about chemical weathering. Alterations that can be caused by chemical weathering are the decomposition of unstable minerals, the generation and retention of materials that are stable, and physical changes such as rounding of the corners or edges. So again, remember, mechanical weathering is breaking down the pieces into smaller, more manageable surface areas where chemical weathering can then go in and attack those smaller surfaces. Alright, so we're going to talk about rates of weathering. So the advanced mechanical weathering aids chemical weathering by increasing our surface area. So we have other important factors to include. So we have rock characteristics. So marble, which has a lot of calcite in it. Remember, calcite is going to react with hydrochloric acid and slowly dissolve. We also have silicate minerals that weather in the same order as their crystallization. So when we think about this right here, think about Bowen's reaction series. So we have our olivine, our pyroxenes, our amphiboles, our calcium feldspars, our plagioclase feldspars. As you're coming down and you get all the way down there and you have your muscovites and your quartz all the way at the end, that is what it's talking about as they weather in the same order of their crystallization. So olivine is the first to form. It's going to be the first to weather. Next is going to be our pyroxenes and our amphiboles, and then eventually you'll get all the way down so that you only have your felsic or your non-ferromagnesian silicates such as quartz and muscovite, and those are going to be the last ones to weather. Now we're talking about these rock characteristics. So when I think of marble dissolving weakly in acidic solutions, think about when you've visited old grave sites and you can have two different headstones from about the same time of two very different materials. The ones that are made of marble, you can hardly read anything on there, whereas the ones that are made of granite, you can see a lot more of the detail. Alright, now with climate, temperature and moisture are the most crucial factors. So chemical weathering is most effective in areas of warm temperatures and abundant moisture to take place a little bit faster. You'll also get a lot more acid rain where you have these sorts of climates. Now differential weathering, we have masses of rocks that do not weather uniformly. We have, we're actually creating many unusual and spectacular rock formations and different landscapes. All right, so just a question to ponder is because of burning fossil fuels such as coal and petroleum, the level of CO2 has been increasing in the atmosphere pretty steadily for about the last 150 years. So will this have an increase, a decrease, or no change at all to the rate of chemical weathering? Any thoughts? So you're adding more acids. So we already have minerals that are dissolving in it. It's actually going to enhance the rate of chemical weathering and make it speed up. Alright, so this is a great chart that goes over our different rates of weathering and our different factors. So we have up here our rates go all the way from slow to fast, and we have our mineral solubility in water, whether it's low, so quartz is not going to weather very easily. Pyroxene and feldspars are somewhere in the middle, and then calcite, which fizzes with our hydrochloric acid, it reacts very well. Rock structure, that's not something we're going to focus on as much, but then we have climate, we have rainfall and temperature, and then the length of exposure. So we'll mainly pay attention to this, our climate, and the length of exposure. And you can just see how when you have rocks that have a lot of quartz in areas where you don't have much rainfall, it's cold, and the rock's only been exposed for a short amount of time, your weathering rate is pretty slow. Now, as you change those factors, it's going to only speed up. All right, so something else to think about. Let's say we have a granite and a basalt. They're both exposed at the Earth's surface for the exact same amount of time in a wet, hot region. So will mechanical or chemical weathering dominate? Our chemical weathering will, right? So chemical weathering is most effective in this sort of region. All right, so which one is going to weather faster, granite or basalt? Our basalt will, right? Because if you think about the chemical makeup of basalt, the minerals that make it up, when you look at Bowen's reaction series, those are going to be the first to crystallize out. Those are going to be the first to erode, versus granite, those are the last ones to form, and so those are going to be the last to erode. All right, let's move on. All right, so the next section is going to get into sedimentary rocks, so check out the next video. This is just a basic introduction into different things that we need to know about weathering to better understand our rocks. If you have any questions, please let me know.